Let's look at compositions of the trig functions and their inverses. Sometimes the trig function and its inverse undo each other. Here are the 6 relationships we need to know. The sine of the inverse sine of x is x, as long as x is in the interval closed interval -1 to 1. Notice I switched the order. So the inverse sine of the sine of theta is theta, as long as theta is in the closed interval -π/2 to π/2. Okay. We have similar relationships for cosine and inverse cosine compositions, and the same thing with tangent or inverse tangent compositions. The key here is the relationship is true as long as your x is in the proper interval. So you need to memorize and learn all of these relationships. Let's try some examples. Okay, the first one, the cosine of the inverse cosine of 4/5. So we need to look at 4/5 right there. In order to use, it's this relationship, the cosine of the inverse cosine of 4/5. The answer is just 4/5 as long as 4/5 is in the interval -1 to 1. Is it? Yes, it is. It's a little bit less than 1. So this is just 4/5. Let's try a second one. The inverse cosine of the cosine of -π/4. Okay, so we find the relationship we want to use. The inverse cosine of the cosine of theta is theta, as long as theta is in the interval 0 to pi. Well, it's not. -π/4 is definitely not in this interval. So what does that mean? Well, it doesn't mean we can't answer the question. It just means we have to work a little harder to find that answer. Okay. So let's start with this part, the cosine of -π/4. We already know how to find this. -π/4, that's in the 4th quadrant. The cosine of an angle in the 4th quadrant is positive. Okay, so this inside part is just 1 over the square root of 2, positive cosine of π/4. By evaluating the inside part, we've now reduced this to a different kind of problem, and we know how to solve this as well. The inverse cosine of 1 over the square root of 2. Okay, this is a positive number between 0 and 1. So in what quadrant will the terminal side of this angle lie? Right, quadrant 1. Okay, so 1 over the square root of 2 is positive, and so this is going to lie in quadrant 1. What angle is it? Well, it's in quadrant 1, so it's a positive acute angle, and its cosine is 1 over the square root of 2, so π/4. And we have one more. The inverse cosine of the cosine of 2π/3. All right, so we go back and we look at our relationship. The inverse cosine of the cosine of theta is theta, as long as theta is in the closed interval 0 to pi. So we need to know, is 2π/3 between 0 and pi? Yes, it is. It's somewhere in the 2nd quadrant, and that's correct. Okay. Here are a few more examples. The inverse sine of the sine of 2π/7. Okay, so we find the relationship that works here, or at least we hope it works. The inverse sine of the sine of theta is theta for any theta in the closed interval from -π/2 to π/2. So the big question here is 2π/7 in that interval, -π/2 to π/2? Okay, so let's think about 2π/7. It's a little bit less than π/2, or half a pi. So it's a little, yes, it's right there. It's somewhere in this interval. Since the answer is yes, then I'm allowed to use this relationship, that the inverse sine of the sine of 2π/7 is 2π/7. All right, let's look at the next one. The sine of the inverse sine of 3/2. Sine of the inverse sine of 3/2, and I see a problem already. 3/2 is too big. It's not in -1 to 1, that interval, so I can't use this relationship. Again, I have to stop and think about whether I can even solve the problem. This number is an angle whose sine is 3/2. Right, that's not even possible. So this expression is undefined. Let's look at one more. The inverse sine of the sine of 2 pi over 3. Okay, so here's our relationship. Inverse sine of the sine of 2 pi over 3 would be 2 pi over 3 as long as 2 pi over 3 is in this closed interval -pi over 2 to pi over 2. But correct, it's not in that interval. 2 pi over 3 is too big. Right, well, when the relationship doesn't hold, we have to stop and think if we can work it out in some other way using other information we know. So let's look at the inside part here, the sine of 2 pi over 3. In what quadrant does 2 pi over 3's terminal side lie? Right, quadrant 2. And we know that in quadrant 2, the sine of an angle is positive or negative? Right, positive. Okay. We could use a reference angle to help a little bit. The reference angle for 2 pi over 3 would be pi over 3. And we know the sine of pi over 3 is the square root of 3 over 2. Okay, so if we fill in just this inside part, we've discovered that the sine of 2 pi over 3 is positive square root of 3 over 2 using this information in our reference angle. We have one more step to finish the problem. The inverse sine of square root of 3 over 2. Okay, inverse sine of this number is an angle, and where does the terminal side of this angle lie? Correct, this is positive, so it's going to lie in quadrant 1. And the angle in quadrant 1, whose sine is square root of 3 over 2, is pi over 3. Let's look at another set of examples. We would like to find the tangent of the inverse tangent of 15. Okay, so the tangent of the inverse tangent of x equals x for any x. This is my favorite one because it's going to have to just be 15. Okay, the second one, the inverse tangent of the tangent of negative pi over 3. Okay, that's this relationship. The inverse tangent of the tangent of an angle is that angle as long as the angle is in this open interval negative pi over 2 to pi over 2. So where will I find negative pi over 3? Inside this interval? Yes. So this one is negative pi over 3. The inverse tangent of the tangent of 7 pi over 12. Okay, so this would just be 7 pi over 12 if 7 pi over 12 is in this interval, negative pi over 2 to pi over 2. Is it? Unfortunately, no. 7 pi over 12 is a little bit bigger than 6 pi over 12, so it's a little bit bigger than pi over 2. This isn't going to work. I have to do something else to find the answer. Well, there's another problem with this one. It's not one of your special angles that you know and love, right? Okay, so we're going to draw some pictures and see if we can figure it out. So we said 7 pi over 12 is a little bit bigger than pi over 2. So 7 pi over 12 has its terminal side in quadrant 2. Well, I know a couple of things about angles in quadrant 2. For instance, would the tangent of 7 pi over 12 be a positive number or a negative number? A negative number. So that might be useful information in a few minutes. I'm just going to make a note of that for now. Okay. What about the reference angle? Can we figure out the reference angle? We'll call that theta r. Do you remember how to find a reference angle? Okay, so this all the way to here would be pi, so we're going to find that theta r is pi minus 7 pi over 12, and that means theta r is 5 pi over 12. Now what? Okay, so we're going to try to find the inverse tangent of whatever this number is, and we know that it's a negative number. So let's think about our inverse tangent function. If you recall, the inverse tangent function has to give you an angle over here between negative pi over 2 and pi over 2. If this is a negative number, then it must be in quadrant 4. Okay, so our answer is somewhere down here in quadrant 4. I'm going to draw that in purple on this one. We want an angle whose terminal side is in quadrant 4, where the reference angle is going to have to match this one, 5 pi over 12. So if I draw that negative angle in the fourth quadrant, the same reference angle as this one, then I find out that the angle is negative 5 pi over 12. In this next example, notice that we're looking for the tangent of the inverse sine of 1 over the square root of 2. So I've sort of mixed up our trig functions and inverse trig functions. None of those special relationships will help us, and we simply need to work this out starting with the inside part. So let's start with the inverse sine of 1 over the square root of 2. This is an angle. In what quadrant does this angle's terminal side lie? Well, since this is a positive number and this is the inverse sine function, it must be in quadrant 1. So this is an angle in quadrant 1 whose sine is 1 over the square root of 2. So you already know what that angle is, don't you? It's pi over 4. Okay. So if we make this substitution, this is just pi over 4, and we've simplified this to being the question just asking what's the tangent of pi over 4, and that's 1. Here we'd like to find the secant of the inverse tangent of negative square root of 3, and again we're going to start on the inside part of this and work our way through. The inverse tangent of negative square root of 3. So this is going to be an angle whose terminal side lies in which quadrant? Okay, well this is negative and this is an inverse tangent, so quadrant 4. And it's the angle in quadrant 4 whose tangent is negative square root of 3. Okay, so have you figured out which one it is? Tangent of pi over 3 is square root of 3. So we want an angle in quadrant 4, a negative angle, whose tangent is negative square root of 3. We're using pi over 3 as our reference angle, so this must be the angle negative pi over 3. So the next question, what's the secant of negative pi over 3? Okay, I think it would be easier for us to find the cosine of negative pi over 3 and use that to get our answer. Where is negative pi over 3's terminal side? Quadrant 4, okay? In quadrant 4, is the cosine positive or negative? Positive. Okay, so it's positive, and we need to know the value. So what's the cosine of pi over 3? 1/2, okay? And we've already decided it should be positive, so this is 1/2. Okay, that wasn't quite my answer though. Cosine of negative pi over 3 is 1/2. So what's the secant of negative pi over 3? 2. And there we go. Let's find the inverse sine of the cosine of 7 pi over 4. So again, we'll start on the inside and work our way through the problem. 7 pi over 4 is an angle whose terminal side lies in what quadrant? The fourth. Okay. Let's just draw a little picture of that. It's going to be down here. 7 pi over 4 is all the way around. Is the cosine of an angle positive or negative in quadrant 4? Positive. Okay. So we're going to be looking for the inverse sine of a positive number. We need to fill that in. What's the reference angle? Pi over 4. Okay, so what's the cosine of pi over 4? Right, 1 over the square root of 2. We've already decided that should be a positive number. Okay. Inverse sine of 1 over the square root of 2. What quadrant can this angle lie in? Its terminal side. The first? Right. In the first quadrant, what's the angle whose sine is 1 over the square root of 2? Correct, it's pi over 4. Let's find the inverse cosine of the sine of 5 pi over 3. We'll start with the inside part, the sine of 5 pi over 3. So tell me about the angle 5 pi over 3. It lands in, its terminal side lands in quadrant 4. What would be the reference angle? Right, pi over 3. Okay. In the fourth quadrant, is the sine of an angle positive or negative? Negative. Okay. So the sine of 5 pi over 3 is negative. Let's figure that number out. We said the reference angle is pi over 3. We know that the sine of pi over 3 is square root of 3 over 2. So this is equal to negative square root of 3 over 2. Okay. So we really need to find now the inverse cosine of negative square root of 3 over 2. Okay, so let's think about our inverse cosine function. The answer here is an angle somewhere in the interval 0 to pi. Since this is a negative number, it means I'm looking for an angle whose terminal side is in quadrant 2 and whose cosine is negative square root of 3 over 2. A reference angle will probably help us here. What positive acute angle's cosine is square root of 3 over 2? Pi over 6. And we're going to draw a picture because we know our angle's in quadrant 2, that our reference angle is pi over 6, and so we know that the angle we're looking for whose terminal side lies in quadrant 2 must be 5 pi over 6. Here we'd like to find the sine of the inverse cosine of negative 7/8. So we'll start on the inside. We're looking for an angle whose cosine is negative 7/8. And where does the terminal side of this angle lie? Well, it's an inverse cosine question, and this number is negative. So in the interval 0 to pi, that must mean we're looking in quadrant number 2. So we're going to sketch the angle in quadrant 2. The terminal side lies here. And we're going to label a point on the terminal side of the angle. And we're going to write down the x, the y, and the r that correspond to our picture. Since we're given the cosine of the angle is negative 7/8 and cosine is x over r, we know that x is negative 7. R has to be positive, so it's just 8. And we'll need to find y. Okay? Well, look at our picture. Y is up here, and that means that y is a positive number since it lands in quadrant 2 here. Okay? So y has to be the positive square root of r squared minus x squared. And when we substitute our known values and work this out, we're going to find out that y is the square root of 15. Okay. Now, unfortunately, I don't know exactly what the value of this angle is, but I have everything I need to know about it. in order to find the sine of that angle. Sine, remember the definition, it's y over r. So the y is square root of 15, and r was positive 8.
Let's take a look at trigonometric identities. An identity is a type of equation where f of x equals g of x for every value of x for which both functions are defined. Look at these examples over here on the left. X plus 1 quantity squared equals x squared plus 2x plus 1. It doesn't matter what value of x you plug into it, the left side will always equal the right side. The same is true for this bottom equation. This is one you should be familiar with. It's one of the Pythagorean identities. Cosine squared x plus sine squared x equals 1 for every value of x. If you plug in, say, x equals pi over 6, cosine squared pi over 6 plus sine squared pi over 6 will equal 1. Again, any value you plug in here for x, you take cosine squared x plus sine squared x, you will always get 1. It's true for all values of x. In contrast, look at these two examples. They're not true for all values of x. We can easily see that by just, say, plugging in x equals 0. We can see on the left that 3 does not equal 6. Same thing on the bottom equation. Cosine of 0 is not squared is not equal to 1/2. These are only true, they're not true all the time. An identity is true for all values of x in the domain. Now there's two important things that you need to be able to do to be successful in establishing identities. One of them is that you need to know the basic trig identities. For example, you need to know the quotient identities, the reciprocal identities, and the Pythagorean identities. And the other thing you need to be able to do is to manipulate expressions using algebra. For example, you need to be able to factor, you need to be able to reduce, you need to be able to get a common denominator. Let's take a look at an example. Here we want to multiply and simplify this expression. Now you need to be careful because there's a negative sign in front of this product, so you need to make sure that you multiply and then you take the opposite of that product. So let's begin. First, we're going to multiply cosine theta plus sine theta times cosine theta plus sine theta. I'm going to put a bracket here in front of my product. So what do we get when we multiply? We're going to get cosine squared theta plus 2 cosine theta sine theta plus sine squared theta all over sine theta cosine theta. Now look inside the bracket. What do you see? I see a cosine squared theta plus a sine squared theta. And again, knowing those basic identities is very important, or you won't be able to recognize that. Cosine squared theta plus sine squared theta is 1, so I'll replace that. Now I'm ready to subtract the bracket, what's inside the bracket, and let's see what we get. We're going to get 1, the 1's are going to subtract out, 1 minus 1. You're going to have the opposite, you're going to have minus 2 cosine theta sine theta in the numerator over sine theta cosine theta in the denominator. And now you recognize that we've got common factors in the numerator and denominator. We can reduce by sine theta and cosine theta and end up with just a negative 2. All right, let's look at another example. Here we want to multiply and simplify this expression. Well, if we didn't have to multiply to simplify, of course, this is just equal to 1, so we could get this. But you're going to see after we multiply that we get a nice expression. Let's go ahead and start. So we want to multiply in the numerator. We're actually not going to multiply it out. We're just going to leave it, this product. Now, what is cosine theta plus 1 times cosine theta minus 1? Of course, that's cosine squared theta minus 1. Now, this should sort of be recognizable to you because you know one of the Pythagorean identities is cosine squared x, or cosine squared theta, let's change this to a theta, plus sine squared theta equals 1. Well, I want to know what's cosine squared theta minus 1. So, of course, if I subtract 1 from this side and subtract, I'm going to get that cosine squared theta minus 1 equals negative sine squared theta. So I can replace the denominator with negative sine squared theta. Now let's take a look. We notice that we have a factor of sine theta in the numerator and a sine theta in the denominator. We can reduce. And so we're left with cosine theta minus 1 in the numerator over negative sine theta in the denominator. So again, many times we'll multiply by some expression of 1 to try to establish the identity to get the other side. All right, let's take a look at establishing identities. Here we want to establish the identity tangent theta plus cotangent theta times cosine theta equal cosecant theta. Well, when we establish an identity, it's important that we work with only one side at a time. In this example, I'm going to work with the left-hand side, so I'm going to rewrite that side. Tangent theta plus cotangent theta times cosine theta. Now in this example, what I'm going to do, which is done many times, is I'm going to change everything to sines and cosines. Remember that tangent theta is sine theta over cosine theta. Cotangent theta, using the quotient identity, is cosine theta over sine theta. Now inside the parentheses, I want to add those terms together, so I need to get a common denominator, which of course is cosine theta, sine theta. Which means that I'm multiplying numerator and denominator here by a sine theta, so I get sine squared theta for the first term, and here I'm multiplying by a cosine theta, so I get cosine squared theta. Look at the numerator, sine squared theta plus cosine squared theta. That should be familiar to you. That equals 1. Now when we multiply, we see that we can reduce by a factor of cosine theta. We get 1 over sine theta. And of course, 1 over sine theta, the quotient identity, the sine and cosecant are reciprocals of each other. So this equals the cosecant, which of course is the right-hand side. So your goal is always to take one side, do algebra to it to get to the other side. All right, let's look at another example. Establish the identity 1 minus secant theta over tangent theta minus tangent theta over 1 minus secant theta equals 2 cotangent theta. What I'm going to do is work on the left-hand side, and we want to combine the terms. We want to subtract, so we have to combine the terms. We need to get a common denominator, which would be tangent theta times 1 minus secant theta, which means that I'm multiplying numerator and denominator here by 1 minus secant theta. So I have 1 minus secant theta times another 1 minus secant theta. So I get 1 minus secant theta quantity squared. And on the second term, I'm multiplying by tangent theta over tangent theta, so I get minus tangent squared theta. Now, we want to square this term. Remember, when you square that term, you're going to end up with 3. We're going to square 1 minus secant theta, and we get 1 minus 2 secant theta plus secant squared theta minus tangent squared theta all over tangent theta times 1 minus secant theta. Now look at the numerator. Remember, one of the Pythagorean identities says that 1 plus tangent squared theta equals secant squared theta. So what you see is secant squared theta minus tangent squared theta. So if I subtract tangent squared theta from both sides, I'm going to get 1. So I can replace all of this with a 1. So let's see what we get. We get 1 minus 2 secant theta plus 1 over tangent theta 1 minus secant theta. And of course, 1 plus 1 equals 2. Now here in the numerator, we've got a common factor of 2. We can factor that out. And now we've got a common factor, numerator and denominator, of 1 minus secant theta. We can reduce by 1 minus secant theta, and we end up with 2 over tangent theta. And remember, the reciprocal of tangent is cotangent, so this is the same thing as 2 cotangent theta, which of course is the right-hand side. So again, what you can see, it's important to be able to square terms. It's important to be able to recognize identities. So the algebra and the trig, very important skills in establishing these identities. Let's look at another example. In this problem, we want to establish the identity 1 minus cosine theta over 1 plus cosine theta equals, parentheses, cosecant theta minus cotangent theta quantity squared. Now remember, when establishing identities, the rule of thumb is to pick the more complicated side. Well, in this case, it's pretty close, so I'm going to choose the right-hand side. But you could start with the left-hand side, and what you would want to do is to multiply by the conjugate of the denominator, which is 1 minus cosine theta. So you'd multiply numerator and denominator by 1 minus cosine theta. I'm going to start with the right-hand side. Cosecant theta minus cotangent theta, quantity squared. Now when you square that, you get cosecant squared theta minus 2 cosecant theta cotangent theta plus cotangent squared theta. Now what I'm going to do at this point is I'm going to change everything to sines and cosines. Cosecant squared is 1 over sine squared. Cosecant, again, is 1 over sine, so I have 2 over sine theta. Cotangent theta, cosine theta over sine theta. And cotangent squared theta is cosine squared theta over sine squared theta. Now let's see what we have. Notice that each of the denominators is sine squared theta, which means we can combine the terms, combine the numerators. We'll have everything over sine squared theta. So we have 1 minus 2 cosine theta plus cosine squared theta. Now look at the numerator. You should notice that that factors, and it factors into 1 minus cosine theta quantity squared. Now looking at the other side, which is always my guide, I see cosines. Remember, you can always write a sine squared theta in terms of cosine squared, because sine squared is 1 minus cosine squared. So now we're almost there. The only thing we need to do is to factor the denominator 1 minus cosine squared theta factors into 1 minus cosine theta times 1 plus cosine theta. And now we can see that we have a common factor of 1 minus cosine theta. We can reduce by a factor of 1 minus cosine theta. And we're left with 1 minus cosine theta in the numerator over 1 plus cosine theta in the denominator, which of course you can see is the left-hand side. That's always your goal, to get to the other side. All right, so remember that sometimes you want to multiply by the conjugate of the denominator, which in this case would be 1 minus 1 minus cosine theta over 1 minus cosine theta. The problem could have been done that way, and you would basically just reverse these steps to get to the right-hand side. All right, let's look at another example. In this problem, we want to establish the identity sine theta minus secant theta over sine theta secant theta equals cosine theta minus cosecant theta. In this problem, I'm going to start with the left-hand side. And what I'm going to do, first let me just write the side. Many times what we want to do is combine the terms. In this problem, what I want to do is separate the terms. So what I'm going to do is separate this into two terms. This is the same thing as sine theta over sine theta secant theta minus secant theta over sine theta secant theta. Because remember, one of the common mistakes a student might make is to think that there's a common factor, but there's not a common factor to each of these three terms. Now, when I separate it into these two terms, I notice that in this term I can reduce by a factor of sine theta to get 1 over secant theta, and here I can reduce by a factor of secant theta and get 1 over sine theta, and then knowing the reciprocal identities, 1 over secant is cosine theta, and 1 over sine is cosecant theta, which of course you can see is the right-hand side. Now, as you can see from these examples, it's very important that you know the basic trig identities very well so that when you see an expression, you know what to replace it with, like sine squared theta plus cosine squared theta equals 1. And you need to go through these examples, practice them until you know how to do them very well without any assistance. Let's take a look at the sum and difference formulas. Here I've listed on the board the sum and difference formulas for cosine, sine, and tangent. Let's see how we can use these sum and difference formulas to find exact values. In this example, I want to find the exact value of the sine of 7 pi over 12, and I'm going to use a sum formula. So the problem is 7 pi over 12, of course, is not one of your special angles. We want to rewrite 7 pi over 12 as the sum of two angles, or the difference of two angles that are special. So I'll write this as the sine of 4 pi over 12 plus 3 pi over 12. Now, of course, that adds up to 7 pi over 12, and what's very important about that is that when you reduce these, you get pi over 3, which of course is a special angle, and pi over 4, which of course is another special angle, so we can find the exact value. You couldn't rewrite this, say, as 5 pi over 12 plus 2 pi over 12, because 5 pi over 12 is not a special angle. So it's very important that when you rewrite it, these two angles are special. So now we have the sine of an angle plus an angle. Well, we can use this identity right here. So in this case, my alpha is pi over 3, and my beta is pi over 4. So using this identity, I can rewrite this as the sine of pi over 3 cosine pi over 4 plus the cosine of pi over 3 times the sine of pi over 4. Don't skip the step where you write the identity. Now we've got it down to trig functions of special angles, and you should know these values very well at this point. So let's plug in those values. The sine of pi over 3, remember, is square root of 3 over 2. The cosine of pi over 4, recall, is 1 over the square root of 2. The cosine of pi over 3 is 1/2. And finally, the sine of pi over 4 is 1 over the square root of 2. So let's see what we get. We get the square root of 3 over 2 square roots of 2 plus 1 over 2 square roots of 2. Since we have a common denominator, we can add and get the square root of 3 plus 1 over 2 square roots of 2. So the sine of 7 pi over 12, the exact value is square root of 3 plus 1 over 2 square roots of 2. Let's take a look at another example. In this example, we want to find the exact value of the tangent of 17 pi over 12 without the use of a calculator. So we're going to use, this time, we're going to think of two numbers that I either add or subtract to get 17 pi over 12. Well, let's see. 17 pi over 12 could be written as 8 pi over 12 plus 9 pi over 12. That certainly adds up to 17. And if I reduce each of these, let's see, that would be 2 pi over 3 and 3 pi over 4. Those are both special. But you could also write it, there's lots of other ways. You could write it as 21 pi over 12 minus 4 pi over 12. If I reduce each of these, let's see what we get. Let's see, 3, that would be 7 pi over 4 minus pi over 3. So the way you rewrite it is not unique. Oftentimes there's more than one way. Let's go ahead and use this way. So we're going to rewrite this as the tangent of 21 pi over 12 minus 4 pi over 12. And that's 7 pi over 4 minus pi over 3. Okay, so now we've got it written as the tangent of alpha minus beta. So we can use this identity right here. My alpha is 7 pi over 4, my beta is pi over 3. So that's going to give us tangent of 7 pi over 4 minus tangent of pi over 3 all over 1 plus tangent 7 pi over 4 times the tangent of pi over 3. Okay, now we just need to find those values. Again, these should be values that you know very well at this point. The tangent is 7 pi over 4. Well, the reference angle is pi over 4. Tangent of pi over 4 is 1, but remember 7 pi over 4 is in quad 4, where the tangent is negative, so this will be negative 1. The tangent of pi over 3 is the square root of 3. So plugging in those values, we get negative 1 minus the square root of 3 over 1 minus the square root of 3. So this is equal to the tangent of 17 pi over 12. In this example, we want to find the exact value of this expression without the use of a calculator. So we look at it, we notice these angles are not special. But look at our identities over here. Which one does this look like? So we see cosine, cosine, plus sine, sine. Well, that looks like this one, doesn't it? So in this case, here's my alpha, and here's my beta. So this could be rewritten as the cosine of alpha minus beta. So we're going to have 7 pi over 12 minus 5 pi over 12. Well, that's the same thing as the cosine, of course, of 2 pi over 12, which reduces to the cosine of pi over 6. And of course, that's much easier to find. Remember, the cosine of pi over 6 is simply the square root of 3 over 2. So I've taken this complicated expression, recognized as one of these identities, and rewritten it. In this example, we're given that the sine of alpha is 3/5. Alpha is between pi over 2 and pi. The tangent of beta is negative square root of 5. Beta is between negative pi over 2 and 0. We want to find the exact value of the sine of alpha minus beta and the tangent of alpha plus beta. Now what's important here is that we draw the angles in the correct quadrant. So notice that alpha is between pi over 2 and pi. So that means that alpha is in quadrant 2. So we're going to draw a picture for alpha in quadrant 2. And we know the sine is 3/5. We know that the sine is y over r. So we know this side is 3, this side is 5. We use the Pythagorean theorem. The third side is 4. But we know since we're in the second quadrant, the x-coordinate is negative. So the x value is negative 4, the y is 3, and r is 5. Now we'll do the same thing for beta. Beta is between negative pi over 2 and 0. Well, negative pi over 2 is here, 0 is here, so we know beta is in quadrant 4. We're going to draw a picture for beta. The tangent is negative square root of 5, so we know the y over x is negative square root of 5. So we know we're going to put square root of 5 on the y, and we're going to put 1 on the x. And again, we know that in the fourth quadrant, the x is positive, the y is negative, and of course the hypotenuse is always positive, r is always positive. Using the Pythagorean theorem, we get this side to be the square root of 6. And now we've got the pictures drawn, we've got all the sides, so now we're ready to begin writing the identity. So let's do part A. We want to find the sine of alpha minus beta. We have to remember that identity goes sine alpha, cosine beta, minus cosine alpha, sine beta. And once we have these values, we can easily find these values pretty easily. The sine of alpha, we make sure that we go to alpha, so it's important that you label them. The sine of alpha is 3/5. Cosine of beta, we go here, x over r, so it's 1 over the square root of 6. Cosine of alpha would be negative 4/5. Remember, x is negative here. And the sine of beta is y over r. I didn't write r here. So the sine of beta would be negative square root of 5 over the square root of 6. Now that we've got our values, we can simply combine. What do we get? we get 3 over 5 square roots of 6 minus 4 square roots of 5, 5 square roots of, over 5 square roots of 6. And since we have a common denominator, we can combine the numerators. So our final answer is 3 minus 4 square roots of 5 over 5 square roots of 6. Now let's look at part B. Now in part B, we want to find the tangent of alpha plus beta. So again, we write the identity for that, which is tangent of alpha plus tangent of beta over 1 minus tangent alpha, tangent beta. And now that we've got our pictures still, we'll just use those to find these values. What's the tangent of alpha? Remember, tangent of alpha is y over x, so we're going to get 3 over negative 4. And the tangent of beta would be y over x, which is negative square root of 5. Now, we can't leave our answer like that because we can't leave complex fractions. So we have to simplify that. And really the easiest way to do that is to multiply, in this case, numerator denominator by 4. So let's see what we get. We're going to get negative 3, and then we're going to get minus 4 square roots of 5. In the denominator, we're going to get 4. And 2 negatives, so we have minus 3 square roots of 5. Now we can leave our answer like that. We can leave radicals in the denominator. We just can't leave complex fractions. So here's our final answer. Now let's look at one final example. In this example, we want to find the exact value of the cosine of the inverse tangent of 4/3 plus the inverse cosine of negative 9 over 41. Well, we can let the inverse tangent of 4/3, we can call that alpha, and we'll call the inverse cosine of negative 9 over 41 beta. And here's where it's very important that you know the range of these inverse functions. Remember, the inverse tangent lies between negative pi over 2 and pi over 2, and the inverse cosine lies between 0 and pi. So you can see it is very important that you know that and not have to look it up. So now what we have is the cosine of alpha plus beta. We'll remember that identity. We need to, again, draw pictures for both alpha and beta. Now, alpha is the inverse tangent of 4/3. Since this number is positive and alpha lies between negative pi over 2 and pi over 2, we know alpha is in quad 1. So we'll draw a picture for alpha. The tangent is 4/3, so the y is 4, the x is 3. And again, we can use the Pythagorean theorem to find the third side, which would be 5. And we'll do the same thing for beta. Beta lies between 0 and pi. This number is negative, so we know it lies in quadrant 2. Cosine is x over r, so the side is 9, the side is 41. And again, we use the Pythagorean theorem to find the third side. Turns out to be 40. So now that we have our pictures, we will write the identity for the cosine of alpha plus beta, which is cosine alpha, cosine beta, minus sine alpha, sine beta, and then we can just plug in our values. What's the cosine of alpha? It will be 3/5. The cosine of beta will be, cosine of beta will be negative 9 over 41. Sine of alpha would be 4/5. And sine of beta would be 40 over 41. So now that we've plugged in our values, we simply determine these values. So that will give you, let's see, negative 27 over 205 minus 160 over 205, which gives you negative 187 over 205 for our final answer. Now in these examples, They illustrate how important it is to know the exact values of the trig functions of the special angles, as well as the range of the inverse function. So be sure you know that. Then practice these examples until you've mastered them. Let's take a look at double and half angle formulas. Here I've listed in this box the identities or formulas for sine 2 theta, cosine 2 theta, and tangent 2 theta. In order to get sine 2 theta, you could use the sum identity for sine alpha plus beta, where alpha and beta are both beta, and you would get this identity. The rest of these identities can be found in a similar way. These two in particular obtained by using the Pythagorean identity. So you need to be familiar with these identities. Let's look at an example where we use one. Here we want to evaluate the expression as the sine, cosine, or tangent of a double angle. That's our first step. Then we want to find the exact value without using a calculator. So look at this. You have cosine squared of 11 pi over 12 minus sine squared of 11 pi over 12. Which one does this look like? Well, notice it looks like this one, where theta is 11 pi over 12. So it looks like cosine squared theta minus sine squared theta. So I can see that theta is 11 pi over 12. So now that I know that, this is equal to the cosine of 2 theta. And we just determined that theta was 11 pi over 12. Well, if you reduce that, what do you get? That gives you, what, 11 pi over 6. So we've taken this expression to values we couldn't find without a calculator to something that we know one of the exact values. This is one of the special angles that you should be familiar with. So here's the first part. We rewrote it as, in this case, the cosine of a double angle. And then do you remember what the cosine of 11 pi over 6 is? Where does the terminal side of 11 pi over 6 lie? Exactly. Quad 4. And cosine in quad 4 is positive or negative? Positive, exactly. So this is the same as the cosine of pi over 6, and those should be values you know. That's the square root of 3 over 2. So first we wrote it as a double angle, cosine of a double angle, and then we found that value. Let's look at this example where we're given sine of theta is 5 over 7, and we know the terminal side of theta lies in quad 2. We want to find the exact value of sine 2 theta, cosine 2 theta, and tangent 2 theta. Well, the first thing we need to do is very important. We need to draw a picture for theta. We know the terminal side lies in quad 2, so let's draw a picture. So here's my angle theta. We know that we need to come up with our coordinates. Well, we know the sine of theta is 5 over 7, and remember that the sine of theta is defined to be y over r. So what I know is y is 5 and r is 7. What we need to figure out is x. Well, we can easily use the Pythagorean theorem to find it, but we need to pay attention. So this point is x comma 5 and r is 7. In quad 2, remember x is negative, so when we find x, it's going to be negative, whoops. It's going to be negative the square root of 7 squared minus 5 squared. What does that give me? 49 minus 25 is what, 24? And remember, we're always asked to simplify radicals if we can. This is the same thing as negative 2 square roots of 6. So now we know x, y, and r. This is very important. Always pay attention to whether x and y are positive or negative in your quadrants. And we know the sine of theta is 5 over 7. We know the cosine of theta would be what? What's going to be x over r? It's going to be negative 2 square roots of 6 over 7. Tangent of theta would be y over x, or negative 5 over 2 square roots of 6. And let's go ahead and write our sign here. It was 5 over 7. So Very important to do this part right, because if you make a mistake here, then the rest of it will be wrong. So now that we've got a picture, let's first find the sine of 2 theta. Well, the identity for that is 2 sine theta cosine theta. And now we just have to plug in our values. Sine of theta, 5 over 7. Cosine of theta, negative 2 square root of 6 over 7. And let's see, what does that give me? Negative 20 square root of 6 over 49. And that can't be reduced. So that's my value for sine 2 theta. Now let's find cosine 2 theta. Well, notice that there's 3 identities for cosine 2 theta. Since we were given the sine of theta, the easiest one to use is the identity that only involves sine of theta. So I will use 1 minus 2 sine squared theta. And then we just have to plug in our value. The sine of theta, remember, was 5 over 7. We want to square that. And remember your order of operations. So we want to square this. We get 25 over 49. That gives me 1 minus 50 over 49. And 1 is the same thing as 49 over 49 minus 50 over 49 gives me 1 over negative 49. So cosine 2 theta is negative 1 over 49. Now let's find the tangent of 2 theta. Well, the identity is 2 tangent theta over 1 minus tangent squared theta. Well, we need to plug in our values. Our tangent was, let's see, where did we write it down? Negative 5 over 2 square roots of 6. Over 1 minus negative 5, 2 square roots of 6, and then that's squared. Okay, so the first thing we need to do, we can reduce this to negative 5 over the square root of 6. And then we got to square this. When you square this, remember you're going to square the numerator and the denominator, so you're going to get 25 in the numerator. And in the denominator, you're going to square 2 and get 4. Square root of 6 is 6. 4 times 6 is 24. And 1 minus 25 over 24, that's 24 over 24, so that's negative 1 over 24. And we can't leave complex fractions. We're asked to simplify that. Remember, that's the same thing as negative 5 over the square root of 6 times the reciprocal. Oops, positive. Times negative 24, which gives me a positive number. I have a negative times a negative. And it's 120 over the square root of 6. So that's my value for tangent 2 theta. One comment about tangent 2 theta. Since we found the sine of 2 theta and the cosine of 2 theta, if you knew both of those, you could have found the tangent 2 theta by doing sine 2 theta over cosine 2 theta. And we already found, because you already had those values. So if you took negative 20 square roots of 6 over 49 divided by cosine, which was negative 1 over 49, this would simplify to negative 20, positive 20 square roots of 6. The 49s will divide out. These two answers are equivalent. So if you don't know the sine 2 theta and cosine 2 theta, then you would just go ahead and use this formula. If you know them, then of course you have a choice. Let's take a look at the half angle formulas. Here I've listed on the board all the half angles for sine alpha over 2, cosine alpha over 2, tangent alpha over 2. Notice for sine alpha over 2, there's 2 formulas. One, if alpha over 2, the terminal side lies in quad 1 or 2, and negative square root of 1 minus cosine alpha over 2 when alpha over 2, the terminal side lies in quad 3 or 4. So it's very important to first know where alpha over 2 is and pick the correct formula. Same thing for cosine and tangent. Although for tangent, notice the last two. Here, same thing, you'd have to know where alpha over 2 lies. But the last two, alpha over 2 can be in any quadrant. Let's look at an example. We want to use a half-angle formula to evaluate cosine 7 pi over 8 without using a calculator. Notice 7 pi over 8 is not a special angle. So it says use a half-angle formula. So that means that 7 pi over 8 is the half angle, so alpha over 2. And from this we can determine what alpha is. If we multiply both sides by 2, then we see that alpha is 7 pi over 4. Now, so we want to find the exact value of 7 pi over 8. So we've determined alpha. We have to choose the formula. So where does 7 pi over 8 lie? Think about that. 7 pi over 8 is a little less than pi, so it's in quad 2. Cosine in quad 2 is negative, so we would choose this formula. So you write down the formula. It's 1 plus cosine alpha over 2. A lot of students make the mistake of choosing the sign based on alpha. Don't do that. You always choose the formula based on where alpha over 2 is. Always write down the formula and then plug in your value. We found alpha to be 7 pi over 4, so we want the cosine of 7 pi over 4. Don't skip any steps. And then you have to find the cosine of 7 pi over 4. Well, 7 pi over 4 lies in what quadrant? 7 pi over 4 is in quad 4. Cosine in quad 4 is positive. So this means this is going to be positive. Cosine of 7 pi over 4 is the same thing as cosine of pi over 4, which is 1 over the square root of 2. Now, we can't leave complex fractions. We need to simplify them. In order to do that, what you're going to do is you're going to multiply underneath the radical by the square root of 2 over the square root of 2. And so what does that give me? Well, 1 times the square root of 2, you get the square root of 2 plus 1 in the numerator. And in the denominator, you get 2 square roots of 2. So the cosine is 7 pi over 8 is negative square root of square root of 2 plus 1 over 2 square roots of 2. In this example, we're given the tangent of alpha is 5 over 12. We're told that alpha is between pi and 3 pi over 2. And we want to determine the exact value of sine of alpha over 2, cosine alpha over 2, tangent alpha over 2. Well, the first thing we need to do is we need to draw a picture for alpha. We know the terminal side lies in quad. If you're between pi and 3 pi over 2, that means it lies in quad 3. So let's draw a picture for alpha. Okay. We know the tangent of alpha, is 5 over 12. And remember, tangent is defined to be y over x. You might be tempted to think both x and y are positive, but they're not. Remember, you're in quad 3, and in quad 3, x and y are both negative. So that means that x is negative 12, and y is negative 5. We use the Pythagorean theorem. We get r to be 13. So now that we know our x, y, and r, we can find, for example, what's the cosine of alpha? Well, it would be negative 12 over 13. Sine of alpha is negative 5 over 13. And tangent, well, tangent we already know. Tangent is 5 over 12. Okay, so now that we know this, let's start with the sine of alpha over 2. Well, the first thing we have to do is we have to pick a formula. And remember, we picked the formula based on where alpha over 2 is. This is a picture for alpha. Where's alpha over 2? Well, what we can do is take this expression. We know that alpha is between pi and 3 pi over 2. If we divide this inequality by 2, that will tell us where alpha, the terminal side of alpha over 2 lies. So we can see that the terminal side of alpha over 2, if you're between pi over 2 and 3 pi over 4, what quadrant is that? quad 2. So that's how we decide. We know the terminal side of alpha over 2 lies in quad 2. We want a sine, and sine in quad 2 is positive, so we choose this formula. Okay, write down your formula, don't skip any steps, and then plug in your value. Cosine of alpha is negative 12 over 13. So underneath the radical, you have 1 plus 12 thirteenths. Well, 1 is 13 thirteenths plus 12 thirteenths gives you 25 thirteenths. And that's the same thing as 25 over 26, which can be simplified because the square root of square root of 25 is 5. So the sine of alpha over 2 I get to be 5 over the square root of 26. Now let's find the cosine of alpha over 2. Well, we've already determined, remember, that alpha over 2, the terminal side lies in quad 2, and cosine in quad 2, is that positive or negative? Negative, exactly. So you're going to use the negative square root of 1 plus cosine alpha over 2. And then you plug in your value for cosine. Let's see, I'll go this way. Cosine of alpha was negative 12 over 13. And so what is that? That's 13 over 13 minus 12, so that's 1 over 13 over 2, which is the same thing as 1 over 26. And square root of 1, of course, is 1, so this is negative 1 over the square root of 26. So now we found the cosine of alpha over 2. Last, let's find the tangent of alpha over 2. Well, since we have a choice on this identities, let's use one where we don't have to choose whether it's positive or negative. Let's use this one, 1 minus cosine alpha over sine alpha, and then plug in our values. Cosine of alpha was negative 12 over 13. Sine of alpha was negative 5 over 13. So again, this is the same thing as 1 plus 12 thirteenths, which is 13 over 13 plus 12, so that gives me 25 over 13 over negative 5 over 13. That's the same thing as 25 over 13 times negative 13 over 5. And that gives you, what, negative 5? For tangent alpha over 2. So the tangent of alpha over 2 is negative 5. Let me point out, it's very important. This part of the step is very important. If you draw the picture wrong, if you don't pay attention to x, y, whether they're positive or negative, you'll make a mistake, and of course all this will be wrong. So pay special attention when you're drawing your picture. Make sure you choose the right formula based on where alpha over 2 lies. Make sure you plug in the values. In this example, we want to find the exact value without using a calculator. So look at this first example. We have the sine of 2 inverse cosine of negative 1/3. First, we want to look at this, the inverse cosine of negative 1/3, and we're going to think of that as an angle. We're going to call it theta. So we're going to let theta be the inverse cosine of negative 1/3. Which means, if you rewrite that, that's the same thing as the cosine of theta is negative 1/3. But remember your range for inverse cosine? Where does this angle lie? What interval? Do you remember? Yes, 0 to pi. So theta must be between 0 and pi. And we know the cosine is negative, so where is it? That's either quad 1 or quad 2. So we know theta lies, the terminal side, in quad 2. So we can draw a picture for this angle. Well, since we know the cosine is negative 1 over 3, we know cosine is x over r. So I know x is -1. I know r is 3. We need to find y. Now notice in the second quadrant, the y coordinate is positive. So it's going to be positive square root of 9 minus 1, which is square root of 8, which simplifies to 2 square roots of 2. So now we found x, y, and r. Knowing that, so let's go back to this problem. We have the sine of 2 theta. Well, we can use an identity. Remember the identity for sine 2 theta? It's 2 sine theta cosine theta. So we need to know the sine of theta and the cosine of theta. Well, we already know the cosine of theta is -1/3. Since we found r, what would the sine of theta be? It would be 2 square roots of 2 over 3. So we can plug in those values. 2 square roots of 2 over 3 for sine theta, cosine -1/3. And so I get a -4 square roots of 2 over 9 for sine 2 theta. Well, let me scoot this over. So once again, it's important to draw the picture. You have to remember your range for inverse cosine and draw it in the correct quadrant. So now we know sine 2 theta is -4 square roots of 2 over 9. Let's look at another example. We want to find the exact value here as well. We see the sine of 1/2 inverse tangent of -1. Well, once again, look at this inverse tangent of -1. Think of it as an angle. We're going to call it alpha. We're going to let alpha be the inverse tangent of -1. And again, what does that mean? It means the tangent of alpha is -1. And again, you have to remember the range for inverse tangent. Very important. Do you remember what the range is? Alpha has to be between where? -pi/2 and pi/2, which means the terminal side either lies in quad 4 or quad 1. Well, we know the tangent is negative, so we know that the terminal side lies in quad 4. And remember, the tangent is y over x. So we're going to have to figure out our coordinates again. Well, let's see. In quad 4, which value is negative? The y, right? So we know y is negative. Well, we'll let y be -1 and x be 1 so that the tangent is -1. Use the Pythagorean theorem. R is going to be the square root of 2. So now we know cosine of alpha is 1 over the square root of 2. And if we need the sine, it would be -1 over the square root of 2. So we've got our values. We've paid attention to what quadrant. And now we're ready to go back to here. So we want to know the sine of 1/2 alpha. That's the same thing as the sine of alpha over 2. Well, remember, there's two formulas for the sine of alpha over 2. There's this one, and then there's this one. Oops, negative. And remember, you choose this based on where alpha over 2 is. Well, we've drawn a picture for alpha, not alpha over 2. But notice that where's alpha? We said it's in quad 4. So we actually know that alpha lies between -pi/2 and 0 because we've narrowed it down to just quad 4. We can divide this inequality by 2 to figure out where the terminal side of alpha over 2 lies. So let's see, alpha over 2 is between -pi/4 and 0, so that means that the terminal side of alpha over 2 lies also in quad 4. And remember, sine in quad 4 is, which one do I use, positive or negative? Quad 4, sine is negative, so I would use this one. Let me write it down here. So it's going to be 1 minus cosine alpha over 2. And again, plug in your value for cosine alpha, which is 1 over the square root of 2. And once again, since we have a complex fraction, we need to simplify by multiplying by the square root of 2 over the square root of 2 underneath the radical. So the sine of this alpha over 2 is what? Let's see. Be the square root of 2 minus 1 over 2 square roots of 2. So again, very important that you know the range for the inverse functions, that you draw the picture, you pay attention to whether x and y are positive or negative, and don't skip any steps. I see students skipping steps and they make a mistake, so make sure you write down the formula and then plug in your values. Practice working these examples until you've mastered the skills and concepts involved.
Today we're going to look at trigonometric equations. A trigonometric equation has a trig function as part of the equation, and there are two types: an identity, which we studied previously, and conditional equations, which we're going to study today. Let's review a minute. What is an identity? An identity is true for all solutions of the variable. Now I'm going to write two examples on the board, and I want you to be copying these because we're going to need them in some other examples. So the first one that you should recognize is the sine of theta squared plus the cosine of theta squared equals 1. This is our famous Pythagorean identity, and we will use it. The second one that I'm going to write here, be copying, remember, is the cosine of 2 theta equals 2 cosine of theta squared minus 1. So what is a conditional trigonometric equation? Where identities are true for all solutions of the variable, a conditional trigonometric equation is only true for specific values of the variable. The example that we're going to start with today is this one. 2 cosine theta plus 1 equals 0. We will get started in just a minute. We're going to look at trigonometric equations that are linear in form. The example that we spoke about earlier is 2 cosine theta plus 1 equals 0. And we want to do two things from our directions. We want to determine a general formula for the solutions of the equation. We're going to let k represent any integer. And then as a B part, we're going to determine the specific solutions, if any, on the interval 0 to 2 pi. So in looking at this equation, the first thing you might ask yourself is, what do I do with it? I don't know where to begin to solve this equation. So you might come here on the side and use substitution. You could use any letter, U or X or Y or W, and let that be the trig function. Making the substitution, you should see an equation that you recognize from algebra. What do we do to solve this equation? Well, very simply, we subtract the 1 and then we divide by 2 on both sides of the equation. So in algebra, we would have this solution. So now, what do we do with our trigonometric equation? The exact same thing. We're going to subtract 1 and then divide by 2. Okay, unlike the algebra equation where we were finished, we now have to solve for the variable theta. We now want to find the general formula for all of the solutions. Well, in order to do that, we need to do a couple of things. First thing we need to do is find the reference angle, theta r. So I'm going to locate, let's remember our right triangles, and let's remember that the cosine function is the ratio of the adjacent side, so we're going to let 1 be the adjacent side, 2, ratio of the adjacent side over the hypotenuse, so we have 1 divided by 2. That means the opposite side is the square root of 3. Okay, what is that reference angle? Well, it is pi over 3. Now, in this problem, our ratio is negative, so pi over 3 is not one of our answers. Which two quadrants is the cosine function negative? Quadrant 2, which will give us one solution, and quadrant 3, which will give us a second solution. Okay, reference angle, pi over 3. Now, let's see what the general formula is. The angle 1, quadrant 2, we will find by subtracting the reference angle from pi. So we have pi minus pi over 3, which is 2 pi over 3, plus the period of our cosine function is 2 pi, and we will multiply that times k. Okay, this will give us a set of solutions. What about the second angle, theta 2? Well, in quadrant 3, theta 2 will be pi plus the reference angle. So that'll be pi plus pi over 3, which is 4 pi over 3 plus, again, 2 pi times k. And that is the answer to the A part of our problem. What do we do for the B part? We want to find specific solutions on the interval from 0 to 2 pi. All we have to do, we're going to begin by letting k be 0. 0 times 2 pi, of course, is 0. That's going to give us a solution of 2 pi over 3. Same thing, let k be 0 here. That gives us 4 pi over 3. Okay, so do we let k be 1? Well, let's see what happens. If k is 1, then we would be adding 2 pi to each 2 pi over 3 and 4 pi over 3. Both of those answers are not in our interval 0 to 2 pi. So we see that on that given interval, we have 2 solutions. Let's look at this example. We want to determine a general formula for the solutions of the equation tangent theta plus 1 equals 0. In our formula, we're going to let k represent any integer. And then in the B part, we're going to determine the specific solutions, if any, on the interval 0 to 2 pi. Now, this example is an example of a trigonometric equation that is linear in form. And when we first look at it, you may not be sure exactly what to do with it. So you can very easily come here to the side, let u be your trig function, tangent theta. Making the substitution, we have the equation u plus 1 equals 0. And solving, we subtract 1 from both sides. We see that u is negative 1. We're going to do the exact same procedure for our trig equation. We're going to subtract 1, And then we want to find all the solutions of theta. The ratio is negative, but to work this problem, we're going to first find the reference angle. So let's come over here to the side and find theta r. In our right triangle, we're going to set up, tangent is the ratio, let's rewrite that here. Tangent of theta bar equals positive 1. We want to know where the tangent is positive. So tangent is the ratio of the opposite side to the adjacent side. Those sides are each 1. By Pythagorean theorem, the hypotenuse is now square root of 2. And we recognize the reference angle to be pi over 4. Back to our problem. Tangent theta is negative 1. Okay, where is the tangent of theta? Negative. There are 2 quadrants in which the tangent function is negative. Quadrant 2, we'll call it theta 1. Quadrant 4, we'll find that solution and call it theta 2. To find the first angle in quadrant 2, we need to subtract the reference angle from pi. So pi minus pi over 4 is 3 pi over 4. And then quadrant 4, we want to subtract the reference angle from 2 pi. 2 pi minus pi over 4 is 7 pi over 4. So we come back here and we want to write our general formula. We have 3 pi over 4 plus pi k, because the period of the tangent function is pi, and 7 pi over 4 plus pi k. Okay, but looking at this, this doesn't seem very concise, and it's not, because if we let k be 1 and add pi to 3 pi over 4, we end up with 7 pi over 4. So the better way to write the general formula is simply 3 pi over 4 plus pi k. That will be our answer for the A part, the general formula. Now, in the B part, we will begin by letting k be 0. That, of course, gives us 3 pi over 4. Let k be 1, as we previously said. Pi plus 3 pi over 4 is 7 pi over 4. But can we let k be 2? I don't think so. 2 pi plus 3 pi over 4 is outside of our interval. We have 2 solutions, 3 pi over 4, 7 pi over 4. What you want to remember about this problem is that when you're solving with the tangent function, you're going to work it very differently than if your trig equation has the sine or the cosine function. We're going to look at this example. The sine of 2 theta equals 1 over the square root of 2. Our directions tell us to find the specific solutions, if any, on the interval from 0 to 2 pi. Now, this trig equation is linear in form, but it's a little different than some of the others that you may encounter in your homework. And that's because there is a constant multiplied times our angle theta. So what we want to think about is what solutions of this angle, what solutions when we take the sine of that angle will equal 1 over the square root of 2. Back here at the side, we can find the reference angle, but you may know it immediately because 1 over square root of 2 sine function is it's in our family and is very obvious to us. Sine function, ratio of the opposite side to the hypotenuse. We see the reference angle is pi over 4. I am going to set this up using a general formula to begin with, even though the problem does not call for me to give that in my final answer. So we'll write 2 theta equals pi over 4 plus 2 pi k. Now that's only one quadrant in which the sine function is positive. Okay, let's think about this. Which other quadrant is the sine function positive? Quadrant 2, correct. That will give us a second solution, which we will find by subtracting the, watch the mistake here. Theta 2 is pi minus the reference angle. So pi minus pi over 4, which is 3 pi over 4. Now, if we did not have this 2, we would be done as far as finding a general formula. But we have to deal with the 2. The 2 is multiplied times theta. We need to take it to the other side, so we're going to divide. It's very important that we divide all 4 terms by the 2. Pi over 4 divided by 2 is pi over 8. 2 pi k divided by 2 is pi k. 3 pi over 4 divided by 2 is 3 pi over 8. And again, 2 pi k divided by 2 is pi k. Now we can start finding our specific solutions. We let k be 0. That gives us pi over 8, then 3 pi over 8. Then we'll let k be 1. So we're adding pi over 8 plus pi, which is 9 pi over 8. Let k again be 1, add pi plus 3 pi over 8. That gives us 11 pi over 8. And of course, we cannot let k be 2 because we'd be adding 2 pi to each of the angles, which is outside of our interval. So we see in this example that we have 4 solutions. We're going to look at a trigonometric equation that is quadratic in form and attempt to solve it. Our directions tell us to find the specific solutions, if any, on the interval from 0 to 2 pi. And our example reads 3 times the cosecant of theta squared minus 4 equals 0. I'm not sure how to begin the problem, so I'm going to come here to the side, let u equal my trig function, cosecant theta. Making the substitution, I have 3u squared minus 4 equals 0. Then I recall from algebra, I would add the 4, divide by 3, and then one more step. To undo the square, I would take the square root on both sides, but I need positive, negative square root of 4/3. And of course, this simplifies to 2 plus or minus 2 divided by the square root of 3. I'm going to do the same thing over here. I'm going to add the 4, divide by 3, take the square root, and I end up with the cosecant of theta is plus or minus 2 divided by the square root of 3. I need to solve for theta. I'm going to find the reference angle. Come here to the side. I'm going to find the reference angle such that the cosecant of the reference angle equals the positive ratio 2 divided by square root of 3. In quadrant 1, my reference angle, I'm going to place the 2 and the square root of 3 at the appropriate sides. I know cosecant is the ratio, cosecant of theta is the ratio of the hypotenuse, so that's the 2, divided by the opposite side, which is square root of 3. That makes this side 1, and I know that my reference angle is pi over 3. Okay, that'll give me one solution. Let's write that solution down for positive 2 over square root of 3 in quadrant 1. But consider this. Cosecant is positive in quadrant 1. It's positive in quadrant 2. It's negative in quadrant 3. And negative in quadrant 4. So we have 4 solutions. Okay, pi over 3 is our solution in quadrant 1. Let's call it theta 1. Theta 2, our second solution, we will find by subtracting the reference angle from pi, which gives us 2 pi over 3, our second solution. Third solution, in quadrant 3, we will find by adding pi to the reference angle, pi plus pi over 3 is 4 pi over 3. Third solution. Finally, in quadrant 4, we will get our solution by subtracting the reference angle from 2 pi, and that gives us 5 pi over 3. This trigonometric equation that is quadratic in form has 4 specific solutions on the interval from 0 to 2 pi. We'll take a look at this example. We want to determine the specific solutions, if any, on the interval from 0 to 2 pi of the trigonometric equation that is quadratic in form, and our example reads 2 times the sine of theta squared plus the sine of theta equals 0. I'm going to make my substitution and let u be the sine of theta, so I can readily recognize how to solve this equation. In algebra, substituting u here, if u is the sine of theta, then sine of theta squared will be u squared, plus u equals 0. Then I recall from algebra, when I have this on the left side of the equation, I can factor the common factor u, and after doing that, u times 2u plus 1 equals 0. The two factors give me 0, so I can set each factor equal to 0 and solve independently. First solution is u equals 0. Second solution is u equals negative 1/2. I subtracted 1, then divided by 2. So that's what we want to do with this trig equation. The common factor is the sine of theta. Write that, then divide. Sine of theta into 2 sine squared is 2 sine theta, plus sine of theta into sine theta is 1. Or you can simply look at what you have here and just substitute back. For u equals 0, we have sine theta equals 0, like this factor, and then 2 sine theta plus 1 equals 0. Solving this one, sine theta equals negative 1/2. We have now two trig equations that are linear in form to solve and get solutions for. Sine of theta equals 0. Now, that's not going to produce, if we were looking for a reference angle, it's not going to produce pi over 3, pi over 4, or pi over 6 are special angles. Because if the ratio for the sine function is the opposite over the hypotenuse, that will not form a triangle. So what I need to look at is the graph of my sine function. Let's graph from 0 to 2 pi. Just a quick sketch, and then we will look and see where is the sine function 0. Sine function is 0 looking at the x-axis, or the x-intercepts, is 0 at 0, pi, 2 pi, 3 pi, 4 pi, and continues. But we only want the solutions from 0 to 2 pi. Notice we do not want to include 2 pi. So for this equation, sine theta equals 0, we have two solutions, at 0 and at pi. Okay, this equation now, we have the ratio of negative 1/2. So we'll come to the side and find our reference angle. We're looking for pi over 3, pi over 4, or pi over 6. So we want to solve the equation. The sine of theta r equals positive 1/2. Sine function, opposite 1, hypotenuse 2, adjacent side square root of 3. So the reference angle, pi over 6, that's right. But back to our problem. This ratio is negative, so we don't want an answer of pi over 6. We want the two quadrants where the sine function is negative. Quadrant 3, that will give us a solution. Quadrant 4, that will give us another solution. Quadrant 3, we need pi plus the reference angle, pi plus pi over 6, which will give us 7 pi over 6. And then in fourth quadrant, an answer for theta will be 2 pi minus the reference angle, which is 2 pi minus pi over 6, 11 pi over 6. Okay, this particular equation then has 4 solutions. Sometimes in writing your solutions, you may be asked to put the solutions in ascending order. Okay, so just double check 0, pi, then 7 pi over 6, then 11 pi over 6. And that is our final answer for this particular example. We're going to look at an example of a trigonometric equation that we will solve using identities. Our directions tell us to determine the specific solutions, if any, on the interval from 0 to 2 pi. And our example reads, -3 times the sine of theta plus 3 equals 2 times the cosine of theta squared. The first thing we notice about this example is that we have the sine of theta and cosine of theta, 2 different trig functions. So what we need to do is find an identity that we can change either sines into cosines or cosines into sines. Let me think. We have an identity that says sine squared theta plus cosine squared theta equals 1. Oh, that's a good one to use. We have the cosine of theta squared, so let's solve for the cosine of theta squared by subtracting the sine of theta squared from both sides. Then we can take this 1 minus sine of theta squared and we can substitute it for the cosine of theta squared. I am going to put parentheses here to enter 1 minus the sine of theta squared, because I'll need to come back and distribute the 2. Let's do that. -3 sine theta plus 3. 2 times 1, 2 times negative sine of theta squared. Okay, let's see what we're going to do now. We need all of the terms on one side of the equation set equal to 0 so we can factor. The squared term, sine of theta squared, has a -2 in front. So I'm going to take that term to the left side of the equation by adding 2 sine of theta squared. Copy -3 sine of theta. And then subtract 2 from both sides. 3 minus 2 is +1. So we have a trigonometric equation that is in quadratic form, and we can factor. I notice the factors of 2 sine theta squared will be 2 sine theta and sine theta. Factors of 1 are 1 and 1. And then we need minus in both of those factors. Checking, this is negative sine theta. This is negative 2 sine theta, which is negative 3 sine theta. Now, if you had to, you could come to the side and make a substitution for sine theta. And you would get the same factorization. But it might make it a little easier for you. Once we have our two factors set equal to 0, all we have to do, let's erase this, is solve each factor separately. 2 sine theta minus 1 equals 0. Set that factor equal to 0. Then set this factor, sine theta minus 1, equal to 0. Sine theta will then equal add 1, divide by 2. Here, add 1. Okay. Sine theta equals 1/2. We'll come to the side, find the reference angle, and then find the two quadrants in which the sine function is positive. Sine of the reference angle equals positive 1/2. Quadrant 1, opposite side over hypotenuse. The adjacent side then is square root of 3. And the reference angle is pi over 6. Okay, that will give us one solution. Because this ratio is positive, sine function's positive in quadrant 1. Same thing as the reference angle. Which other quadrant is the sine function positive? Well, that's quadrant 2. That will give us a second solution. We find that angle by subtracting the reference angle from pi, pi minus pi over 6 is 5 pi over 6. These are two solutions, solves this equation on this interval. Now we'll go to this part. Sine theta equals positive 1. We don't have a reference angle of pi over 3, pi over 4, pi over 6 for the sine of theta equals 1. What we need there is the graph of our sine function. So I'm going to graph from 0 to 2 pi. Oh, let's do this a little better. Let's do this a little better. There we go. That looks better. So our range from -1 to 1, we notice that the sine of theta equals positive 1 at pi over 2. So, summarizing, and we're going to write our final solution. On the interval from 0 to 2 pi, we have 3 answers. Pi over 6, 5 pi over 6, pi over 2. I'm going to write the 3 solutions in ascending order. So I'm going to write pi over 6, pi over 2, and 5 pi over 6. Again, to solve this equation using identities, we made a substitution for cosine theta from our Pythagorean identity. This example involves us solving this trigonometric equation, cosine of 2 theta minus 3 equals negative 7 times the cosine of theta. Our directions tell us to determine the specific solutions, if any, on the interval from 0 to 2 pi. We're going to use an identity because this trig function, cosine 2 theta, is different than this one, which is the cosine of just theta. I want to use the identity for the cosine of 2 theta. There are actually 3 versions to this identity. We have cosine squared minus sine squared. We have 1 minus 2 sine of theta squared. And we have 2 cosine of theta squared minus 1. So I want to choose the one that will work the best for this problem. Since the equation has a cosine of theta function, we will use this version. I'm going to substitute 2 cosine of theta squared minus 1 for the cosine of 2 theta. Let's do that. 2 cosine of theta squared minus 1 minus 3 equals negative 7 cosine of theta. At this point, I need to combine like terms. I need to take the negative 7 cosine of theta to the left side, set the whole equation equal to 0. 2 cosine of theta squared plus 7 cosine theta. A negative 1, a negative 3 gives me negative 4. I have the terms in descending order, so I can factor. This factoring, I'm not sure what to do. Let me let u equal the cosine of theta. 2u squared plus 7u minus 4 equals 0. I know the factors of 2u squared are 2u and u. And I think the factors that I'm going to need for 4 are 4 and 1, with a plus sign here, minus sign there. Double check on the outside, I have 8u. On the inside, I have negative 1u. That combines to positive 7u. Let's just make the substitution now with cosine theta. 2 cosine theta minus 1 times cosine theta plus 4. Once I have the product of these two factors set equal to 0, I can set each factor equal to 0 and solve. Two cosine theta minus 1 equals 0. I'm going to add 1 and divide by 2. Cosine theta plus 4, I simply subtract the 4. Cosine of theta equals 1/2. This is a positive ratio, so once I find the reference angle, I know that will be one solution to this equation on my given interval. But let's find the reference angle so we can find the second solution. Cosine of theta r equals positive 1/2. Setting up our triangle, I know that the cosine function is the ratio of the adjacent side, I place the 1, divided by the hypotenuse, so I place the 2, and I know that the opposite side is square root of 3. So the reference angle is pi over 3. Okay, where else is cosine function positive? Quadrant 4. That angle we will find by subtracting the reference angle from 2 pi, which gives us 5 pi over 3. So these are the pi over 3, the 5 pi over 3 are the first two solutions. Now, let's go to cosine theta equals negative 4. I know it's not pi over 3, pi over 4, pi over 6. So let me go to my graph of my cosine function. Y equals cosine x. Maybe I will find solutions there. Here we go, from 0 to 2 pi. Oh, I see the problem now. The graph doesn't reach negative 4. We know that the range of this function is from negative 1 to 1. So this equation gives us no solutions on our given interval, or ever really. So we have two solutions, pi over 3, 5 pi over 3, on the interval from 0 to 2 pi. Now we want to solve a trigonometric equation using a calculator. Our directions are approximate all solutions to the equation on the interval from 0 to 2 pi. And we're going to round our answers to 4 decimal places. Here is our example. Sine of theta is 78/100. Here's the calculator. First thing we need to know about the calculator is that we put it in radian mode. Make sure you know how to do that. Okay, got that. So let's write that in our notes, radian mode. This ratio is positive, so we want to first find the reference angle. And we're going to do that by entering in our calculator sine inverse of this positive ratio. Okay? So we're going to do second sine, then 0.78, enter, and we get that the reference angle is approximately, let's change that, approximately 0.8947. Okay, I've rounded this 7. There was 6, 6, and then I've rounded to 7. The ratio is positive, so that will give us one solution, our reference angle. The second solution will be found in quadrant 2, which we will find, let's call it theta 2, by subtracting the reference angle from pi. So let's write our solutions. 0.8947, pi minus that number, which according to our calculator is 2.2469. And those are the two solutions for the trig equation sine of theta equals 78/100.
We're going to take a look at solving right triangles. To solve a right triangle means to find the measure of each of the acute angles and the length of each of the three sides. It's a good idea to organize your information from the beginning. There are three sides, and we need to know the length of each. C is the hypotenuse 10, which happens to be given this time. And we have three angles. Angle C is the 90-degree angle opposite the hypotenuse. B is given to be 35 degrees. And A we'll need to find. Now, finding angle A is the easiest thing we can do in this problem because we know that the sum of the three angles in a triangle is 180 degrees. So A is 180 minus the 35 minus the 90 degrees. And if we subtract this, we should come up with 55 degrees. Okay, so what are we going to do next? We need at least one more side before we could think about the Pythagorean theorem or anything, so we're going to have to use trig. We'd like to use one of those 6 trig ratios that we've learned. We have some choices. Let's find B first. B is the side opposite 35 degrees. So which ratio might I use? It kind of depends on what else I know. I know the opposite. I'd like to know the opposite side. I do know the hypotenuse. So now we know which ratio to use, right? The sine of 35 degrees is the opposite side, B, over the hypotenuse. We're going to solve for B, multiply both sides by 10. So we need our calculator. Make sure it's in degree mode. And we want to multiply 10 times the sine of 35 degrees. That is 5.735. We're going to round to 1 decimal place, so this is approximately 5.7, and this is B. We have one more piece of information to find, and that is A. We could use the Pythagorean theorem to find it. We could also use one of our other trig ratios to figure it out. A is the adjacent side to the 35 degrees, and we know the hypotenuse is exactly 10. So we're going to go ahead and use the cosine of 35 degrees to find A. So it's going to be A over 10. Multiply both sides by 10 again. Use your calculator to approximate that to 1 decimal place. This is going to be approximately 8.2, rounded to 1 decimal place. Let's try one more. In this right triangle, we're given 2 sides, and we'd like to solve that right triangle. So here we need to find the third side and the 2 acute angles. Let's start by organizing our information. So A is 5, B is 6, C we don't know yet, and now we have to worry about our angles. We don't know A or B at this point, and we know that C is our right angle. Okay, we can find the hypotenuse C using the Pythagorean theorem, so let's do that first. C squared has to equal 5 squared plus 6 squared. So C is exactly equal to the square root of 61. We'll use our calculator to approximate that to 1 decimal place. And it's about 7.8. Okay. Now, for the angles, we'll have to use some of our trig ratios. Okay, so let's look at angle A. We know the opposite side to angle A is 5 and the adjacent side is 6. So that's our tangent ratio. The tangent of A is 5 over 6. So we want to use the inverse tangent on our calculator to approximate A. The inverse tangent is usually that second function on your tangent button. This is about 39.8 degrees. Do make sure your calculator is in degree mode for that one. Okay. Okay, the only thing left is angle B. It's one of the acute angles in the right triangle. We know that the sum of all those angles is 180 degrees. So that means the sum of these two acute angles is 90 degrees. The easiest way to find B then is to take 90 minus the 39.8 degrees you just found for angle A. And we find out then that B is 50.2 degrees. Solving right triangles has many applications. Here's one. A hawk is sitting on top of a 34-foot pole. It spots a mouse on the ground at an angle of depression of 28 degrees. Find the line of sight distance between the hawk and the mouse. So clearly, before we start, we need to draw some sort of a picture. Here's our 34-foot tall pole that's on the ground. We're going to assume the ground's flat. And right at the top of the pole, there's our hawk. And he's looking, and he finds a mouse. So the mouse is down here. The question asks us to find the line of sight distance between the hawk and the mouse. So we want to know how far is it for the hawk to get to the mouse. Okay, well, we have one other piece of information we need to place on our picture. The angle of depression from the hawk looking down to the ground is 28 degrees. Okay? So an angle of depression is relative to the horizontal, and it's depression, it's going down. Okay? So this is our angle of 28 degrees that we're given. This dotted line, the diagonal one here, that is the line of sight distance between the hawk and the mouse, and this is what we want to find, so let's call it X. Okay? Where's the right triangle? Well, we have to assume that the pole is perpendicular to the ground. So there we go. Okay. Well, there's one other problem. Notice that the 28 degrees is not part of the right triangle that I would like to solve. So we're going to do a little geometry. If this is a right angle, then so is this one. So that means that the 28 degrees and alpha have to have a sum of 90 degrees. So the first thing I'm going to do is subtract 90 minus 28, which is 62 degrees. And so that's alpha, okay? And I can just stop there because alpha is in the right triangle. It's one of my acute angles, and I can use that one, I think, to help me figure out X, okay? So X is the hypotenuse of the right triangle, and I know this leg. This leg is adjacent to angle alpha, and that should trigger cosine. Cosine of this angle is the adjacent side over the hypotenuse. So let's write this down. The cosine of 62 degrees is 34 over X. We know how to solve this, right? Multiply both sides by X. divide both sides by cosine 62 degrees. And we take out our calculator and approximate this to 1 decimal place as requested. So about 72.4 feet is the line of sight distance from the hawk to the mouse. This next example is a little bit more complicated. We have to use 2 right triangles to find a missing piece of information. A monument is spotted at the edge of a cliff at a distance of 300 feet from the base of the cliff. The angle of elevation to the bottom of the monument is 37.8 degrees, and the angle of elevation to the top of the monument is 42 degrees. Find the height of the monument rounded to 1 decimal place. So we need to draw a picture. We're going to draw a sort of simple picture. Here's our cliff, and we're going to put a monument of some person on the top of the cliff. Okay, now imagine that you're standing over here 300 feet away from the cliff, and you look up to the bottom of the monument. And then we're told the angle of elevation to the bottom of the monument is 37.8 degrees. Okay. The angle of elevation to the top of the monument from that same place is 42 degrees. Okay, we're going to assume the cliff is perpendicular to the ground, so we have a right triangle here. We were told we were standing 300 feet away, so let's label the 300 feet. This is really all we know, but we do have some unknowns that will be helpful to us. We're asked to figure out the height of the monument, so the height h is going to be for the height of the monument, and then x is going to be the height of the cliff. Okay. We have 2 right triangles. We know 1 acute angle. Look at the 300 feet. That is the adjacent side to the 37.8 degrees, and it's also the adjacent side in the bigger triangle to the 42 degrees. Okay. Let's concentrate on one of those triangles to begin with. Let's concentrate on the smaller one. What side is opposite 37.8 degrees? That's our x that we don't know. And the adjacent side is 300, so we're going to use tangent, opposite over adjacent. Tangent of 37.8 degrees is x over 300. Okay. Now let's look at the bigger triangle. This one has that angle of elevation of 42 degrees. The adjacent side is still 300. And the opposite side is all of this, the cliff plus the monument, or x plus h. So we can write another equation. Tangent of 42 degrees is the opposite side, x plus h, over the adjacent side, 300. So look at what we have. We have 2 equations with 2 unknowns. We're going to use some algebra to solve for our missing information. Okay. Ultimately, we need to find the height of the monument. And remember, we called that h. So our goal is to find this h. We're going to use substitution. Take this first equation, solve it for x. How do we do that? Multiply both sides by 300. So x is 300 times the tangent of 37.8 degrees. Before I do any substituting, I'm going to do something to this equation as well. I'd like to not have that fraction in my way, so I'm going to multiply both sides of this one by 300 as well. Okay. What can I do? Substitution. X is this expression. I'm just going to substitute this expression for the x right here. Okay, so x is 300 times the tangent of 37.8 degrees. And this should be a plus sign because it's x plus h. And to get h by itself, I need to subtract this expression from both sides. So h is going to be 300 tangent 42 degrees minus 300 times the tangent of 37.8 degrees. Now at this point, you're just using your calculator to approximate it. You can do that from here. You can simplify it first by factoring out the 300 if you choose to. But either way, calculator approximation. So I get 37.417. We were told to round to one decimal place again, so that's about 37.4 feet. Practice working through these examples until you've mastered the skills and concepts involved.
Let's look at how we can solve an oblique triangle. An oblique triangle is a triangle that does not have a right angle, so we don't have the Pythagorean theorem to look at, and we don't have the sine is opposite over the hypotenuse and that sort of thing. So we have other tools to use. And one of the tools we can use is the law of sines. In any triangle, you have 6 parts, and you have these ratios that are always be true. The sine of alpha is to A, as the sine of beta is to B, as the sine of gamma is to C, or you can use the reciprocal. Now, one thing that students tend to have trouble with is when do they use the law of sines? So I'm going to show you a technique that you can use. If you set up a little chart with your sides and your angles listed, and then you check off or fill in the material that you're given, the values that you're given, then you'll know. Anytime you have one side and the angle opposite that side, you have a ratio. You can set up one of these ratios, and then you can find the other missing parts. So anytime you have a side and the opposite angle, you can use the law of sines. There's actually 3 cases. We have the angle, 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 and side angle, and these are the cases that use the law of sines to solve the triangle. Let's solve a triangle using the law of sines. First thing you always want to do is you want to organize your data. If you set up your little chart here, you're going to find that you will be able to solve these much more efficiently because you'll immediately have everything in order. You can see what you have, what you can find quickly, and we'll go from there. So what we have here is we know that C is equal to 65. We're given that alpha is equal to 46 degrees. And beta is equal to 20 degrees. Now, you might say, well, I don't have a ratio here, so how am I going to solve using the law of sines? Because you have to have a ratio. But we have 2 angles, and anytime you have 2 angles in a triangle, you find the third angle very quickly because the sum of the angles is 180 degrees. So we're going to know that gamma is going to be 180 degrees minus 46 degrees minus 20 degrees. So we have an exact value for gamma. It's 114 degrees. So that's one of our missing parts. So now we have that ratio that we said we needed to use the law of sines. So we're going to find sides A and B by setting up the ratio. A is to the sine of 46 degrees. Oops. Now, remember, we use what we're given. So we have that 65 is to the sine of 114 degrees. All right, so A is equal to 65 times the sine of 46 degrees divided by the sine of 114 degrees, and we'll calculate that in a minute. And we're going to do the same thing for side B. So we have this, so now we know that B is to the sine of 20 degrees as 65 is to the sine of 114 degrees. So we can solve for B. B is 65 times the sine of 20 degrees divided by the sine of 114 degrees. So now we can find a decimal approximation for these two, and we've solved our triangle. All right, make sure again that you have it in degree mode, because if you've been working in radian mode and degree mode, you might want to make sure that you double check that, because you could get seriously wrong answers. All right, so we divide by the sine of 114, and we get that A is approximately 51.18. All right, and now we'll find B. So we'll multiply 65 times the sine of 20 divided by the sine of 114. And oops, I got the wrong answer there. I can see that. I got sine in there, so we'll redo it. So we have 65. Part of the thing is in any kind of math is you're going to get the wrong answer. The trick is to know when you've got the wrong answer and check your answers again. So it's not that we don't make mistakes, it's just knowing when you do. All right, so this one works out better. This is approximately 24.34. Now I want to point out something in a triangle. I want you to notice this, because this can help you in other triangles when you're solving problems and make sure you've got your data organized. You'll notice that the largest side is always going to be opposite the largest angle. Smallest side is opposite the smallest angle. So you can kind of give a visual check there and make sure that you've written it down. You might find the right answer and then write it in the wrong place. So if you kind of just do a visual check of that, you'll see that you've got everything as it should be. So now we have solved that triangle. Now we're going to look at something called the ambiguous case within the law of sines. And this is when you have side-side angle. You have an angle, the side opposite that angle, and one other side. If you set it up in your little chart, if you look at this and you have the three sides and the three angles, if you're given one side and the angle opposite that, and either of the other two sides, it doesn't matter, and this can be in any order, then that's what we call the ambiguous case. Now we call it that because you might go back and remember about inverse sines. We know that on your calculator, if you enter sine inverse of 1/2, it's going to give you an answer of 30 degrees. But you have to remember that the sine of 150 degrees is also equal to 1/2. But your calculator's not going to tell you that. But 30 degrees and 150 degrees could both be angles in a triangle. They're both less than 180 degrees. So this creates what we call the ambiguous case. Now, the ambiguous case has three outcomes possible. You can have 0 triangles, you can have 1 triangle, or you can have 2 triangles. But I'm going to show you how you can find that out very quickly. We're going to continue with this technique, and now we'll solve an example using the law of sines ambiguous case. All right, as we always do, we want to take the triangle and the information we're given, and we're going to put it in our chart. So we're told that A is equal to 3, B is equal to 2. We don't have a value for C. We're given that A is equal to, alpha is equal to 40 degrees, and then we have to find beta and gamma. Now, this is the ambiguous case. And remember, how do you know it's the ambiguous case? You're given one side and the angle opposite that side and one of the other two sides. So now we look at this and we say, all right, what's the first thing I can find? Well, obviously I don't have any way of finding C or gamma, but I can use the law of sines to find beta. So I'm going to set up my ratio and we're going to find beta. So I know that the sine of beta is to 2, which is side B, as the sine of 40 degrees is to 3. All All right, now I'm going to solve for beta. This will take a little algebra here, but we know that the sine of beta is 2 times the sine of 40 degrees divided by 3. So beta is sine inverse 2 times the sine of 40 degrees divided by 3. So we're going to find that value. And be careful when you put this in your calculator. Make sure you put parentheses around this whole expression, because otherwise you would definitely get a wrong answer. So we have sine inverse 2 times the sine of 40 divided by 3, and we get 25 point, I think we'll just round it off to 1 decimal, so that'd be 25.4 degrees. So beta is approximately 25.4 degrees. Now, so I know I have at least one triangle because I found beta. All right? So the question is, how do I know if there's one triangle, just this one, or if there's two triangles? Okay, so here's what you do. Remember that the sine of 25.4 degrees is the same as the sine of the supplement to 25.4 degrees. So if I find the supplement of 25.4 degrees, all right, so we have 180 minus 25.4. That's 154.6 degrees. So the sine of 154.6 degrees is this same number in here. Now, so the question is, okay, can that work in this triangle? Well, what would happen if I substituted 154.6 degrees in for this? Let me just erase this here and let's put it here and let's see what would happen. So I'm saying, okay, I found the other angle and I'm good to go. But now I look and I see, oops, I've got 154.6 degrees plus 40 degrees is greater than 180 degrees, and the sum of all of them can only be 180 degrees. So we know that that is not going to be the case, and that the only value for beta in this particular set of data that we're given is 25.4 degrees. And so now we know we only have one triangle, and we're going to find the other two missing parts. Well, we can't find C. Remember, a squared plus b squared is not equal to c squared. So we're going to find gamma using the fact that it's the sum of the angles in the triangle is 180. So gamma, actually we'll put approximately because we're approximating this. So gamma is approximately 180 minus 40 minus 25.4. All right, so that's 114.6 degrees. All right. Now we can find the third side, C. Now remember, don't use beta to find C, because you've already approximated here. You've already approximated here. Use what you're given, more exact values. You'll get a better approximation. You'll get less likely to make a round-off error. So we know that C is to the sine of 114.6 degrees, as 3 is to the sine of 40 degrees. So we can solve for C now. So C is 3 times the sine of 114.6 degrees divided by the sine of 40 degrees. All right, so we'll calculate that. And we get 4.24. Now, let's go back and double check. Remember, we talked about the fact that the largest angle is opposite the largest side. And we see that this is the largest angle, this is the largest side, and that the ratios hold. So now we have found our triangle. We've discovered that in this particular set of measurements that there was only one triangle. So we have solved this oblique triangle. Let's take a look at another example of the ambiguous case. How do I know it's the ambiguous case? Because I have one side, a given angle opposite that side, and one other side. So the first thing that we're going to do is we're going to try to find alpha, because that's all really that I can do. So I'm going to set up my trig ratios for the law of sines. The sine of alpha is to 2 as the sine of 60 degrees is to 1. So the sine of alpha is 2 times the sine of 60 degrees. Now, you might already see what's happening here, but just in case you don't, or it's an angle you're maybe not familiar with, you have 2 times the, alpha is sine inverse of 2 times the sine of 60 degrees. So this is a good chance to review one of our exact value angles. So the sine of 60 degrees is the square root of 3 over 2. So what am I asking here? I'm asking what angle has the sine square root of 3? No angle has sine square root of 3. Remember, sine is always between 1 and negative 1. So this angle does not exist. Does not exist. And so there are 0 triangles given this particular set of measurements. Now let's do an example with the ambiguous case that has 2 triangles, and I want to show you how you can discover that there are in fact going to be 2 triangles. Just from looking at this data, you can't tell. We're going to continue just like we did in the past. The first thing we're going to do is we're going to find this first angle gamma. So we know from the law of sines that the sine of gamma is to 10 as the sine of 35 degrees is to 6. So we have that the sine of gamma, oops, wrote alpha, not gamma, sine of gamma is 10 times the sine of 35 degrees divided by 6. So gamma is sine inverse of 10 times the sine 35 degrees divided by 6. All right, so now we're going to find this first gamma. Again, you got to be careful when you're putting in your values. Make sure you put parentheses around that numerator. So we're going to have sine inverse of 10 times the sine of 35 divided by 6. And we get a value of 72.9 degrees. So let's make that an approximate. That's kind of messy. All right, 72.9 degrees. All right, so we know that we have this triangle. So gamma is approximately 72.9 degrees. Now remember, there's 2 angles less than 180 degrees that have this same sign. So we're going to find, we'll call this one gamma 1. So we're going to find gamma 2. So gamma 2 is 180 degrees minus 72.9 degrees, and that's going to be 107.1 degrees. And we'll just do 1 decimal place. All right, so here's the question. Can we have 2 triangles? Well, if instead of 72.9 degrees, I wrote in 107.1 degrees, question is, could that work? Yes, it can, because 35 plus 107.1 degrees is less than 180 degrees. Now I know I have 2 triangles. So we're going to make another chart here with our data. So we'll put back here, we have that this is 72.9. And now, all right, so this is going to be triangle 1. And we're going to have triangle 2. So we know that A is 6. I'm going to call that beta B1 and this beta 1 and that gamma 1 just to keep myself straight so I don't get confused. So this will be B2. A and C have the same value, so that doesn't change. Alpha is 35 degrees. This will be beta 2. And this will be gamma 2, which we've already found. So that's going to be approximately equal to 107.1 degrees. Now we have our 2 triangles set up, and it's really not going to be very difficult to solve for these missing parts. We can find these 2 angles by subtracting from 180 degrees. So we know that beta 1 is approximately 180 degrees minus 35 degrees minus 72.9 degrees. All right, so we have 180 minus 35 minus 72.9. and that's going to be 72.1 degrees. They're kind of close, and we'll talk about what happens there in a minute. And so then beta 2 is approximately 180 degrees minus 35 degrees minus 107.1 degrees. And let's see what that is. That's 37.9. So this is approximately 37.9 degrees. All right. So we have found everything but these two sides. Now I want to show you something here, and this is kind of a way you can, there's always ways that you can check yourself and, maybe not know exactly, but you can tell if you're kind of going in the right track. Remember we talked about the fact the largest angle is opposite the largest side, and they kind of have these ratios. And you'll notice that these two angles are really close in value. So if I do my work correctly, I would expect that these two sides should be really close in value. And you've got the same thing down here. This is 35, this is 37, not quite as close as they are, but that's going to kind of give you an idea that beta 2 is going to be just a little bit bigger than 6. And this one is going to be just a little bit less than 10. So that'll kind of help you when you're doing your calculations, make sure you don't put something in wrong. So let's find beta 1. Beta 1 is to the sine of 72.1 degrees. Now remember, once again, use what you're given, not what you find. So as 6 is to the sine of 35 degrees, so B1 is 6 times the sine of 72.1 degrees divided by the sine of 35 degrees. All right, so let's see what that is. 6 times the sine of 72.1 divided by the sine of 35. And that's 9.95. And that's what I expected. I wanted it to be close. Now we'll find B2. Again, we're going to use what we're given, not what we found. So we set up that B2 is to the sine of 37.9 degrees, as 6 is to the sine of 35 degrees. So B2 is 6 times the sine of 37.9 degrees divided by the sine of 35 degrees. All right, we'll calculate that. 6 times the sine of 37.9 divided by the sine of 35 is 6.43. Again, that's what I expected. I wanted those to be close because the angles are close. So that's just kind of a visual check you can give yourself. So now we have solved the law of sines case where we have two triangles. Sometimes when you're solving an oblique triangle, you run into a situation where the law of sines doesn't apply. And the question is, well, when does the law of sines not apply? Well, if you think about it, if you put your data down in an organized little chart like this, the law of sines, to use the law of sines, you have to have a ratio. So what happens if I have side A, angle beta, and side C? I can't set up a ratio. There's no way to find side B. There's no way to find either one of these angles, so I don't have any options there. Or if I have all three sides, I'm not going to be able to use the law of sines. So these are the cases. This is the side angle side and the side 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 case. So when this occurs, you use the law of cosines. Now I have all three of these up here, or actually 6 of them. You have a squared is equal to b squared plus c squared minus 2bc cosine alpha. Notice that this is a, this is alpha. And that we have then alpha is cosine inverse b squared plus c squared minus a squared over 2bc. And as you study these, you'll see the similarities between all of them. They're very similar. You just have some letters that are going to change. This is b squared, and this is a and c and beta, and so on like that. Now, I want to warn you about one thing. When you use your calculator to find and you're using cosine inverse, make sure you put parentheses around the numerator and the denominator, and then around the whole expression, otherwise it won't come out for you. So now we're going to look at an example using the law of cosines. Suppose that a is equal to 2 B is equal to 3, and angle gamma is equal to 95 degrees. If we look in this triangle up here and check off the information that we're given, we can see that this is the side angle side. It doesn't always have to be A and then B, beta and then C. So it's the side angle side scenario. So we're going to use the law of cosines to find side C first. All right. So we know that C squared is equal to A squared plus B squared times minus 2AB cosine of gamma. So C is going to be the square root of these values, and we're going to put these in. So that's 2 squared, which is 4, 3 squared, 9, minus 2 times 2 times 3 times the cosine of 95 degrees. So C is approximately equal to, all right, we're going to find what this number is. Now, the reason I'm not going to put a decimal approximation just yet is because when you're entering the values, you want to make sure that when you switch these other values, you want to use as much you want to use as little approximation as possible. So we're going to go ahead and find that. So that value is 4 plus 9 minus 4 times 3 times the cosine of 95. So we're going to say that this is 14.04587. So we're just going to leave it like that. Now we can find an approximation for that and use that as a value for C over here. But when I'm finding alpha or beta, whichever angle I find first, I'm going to use this number. The value of C is approximately 3.75. Now we're going to use the law of cosines to find angle alpha. All right, so alpha is cosine inverse B squared plus C squared minus A squared divided by 2 times B times C. Now you can see why we left this in this notation, because we can square it, get this number here, and then down here we'll use that square root notation. It's a lot to enter in your calculator, but just you have to be careful. So this is cosine inverse B squared, which is 3 squared, 9, plus C squared, which we'll use this approximation, minus A squared, divided by 2 times B times C. All right, be careful when you put this in your calculator. You're going to have parentheses around your numerator and your denominator, and so this is going to take a lot of entering. So let's just do it. We'll just be real careful when we enter it. So it's going to be 14.04587 minus 4. All right, and that's 14.0487. All right, so we get alpha is approximately 32.1 degrees. All right, so now we can find beta by subtracting from 180. So we have 180 minus 32.1 minus 95. And so we get approximately 52.9 degrees. So now we've solved this triangle using the law of cosines. Now we're going to do an example solving a triangle when you're given all three sides. Again, we're going to use the law of cosines. Now, what we're going to do is we're going to find the largest angle first. Sometimes when people use the law of cosines, after they find the first angle, they change to the law of sines. And if you use that technique, then you definitely want to find use the law of cosines to find the largest angle first. All right, so we'll find angle gamma. So gamma is cosine inverse of a squared plus b squared minus c squared times 2ab doesn't look like a gamma, it looks like an alpha. So that's cosine inverse. A squared is 36. B squared is 25. C squared is 64. Divided by 2. AB. A is 6. And B is 5. All right, so we're going to put that in our calculator and find out what alpha is. So it's cosine again. Make sure you put parentheses around the numerator and the denominator when you're putting this in your calculator, or you won't get the correct answer. All right, so for for gamma, we get approximately 92.9 degrees. All right, now, it doesn't really matter which of these other angles we find. I'm going to find alpha, and I'm going to use the law of cosines again. These are all exact numbers. They're easy to enter into your calculator, so it's not going to be too much to worry about. So alpha is going to be cosine inverse of b squared plus c squared minus a squared divided by 2 times b times c. So alpha is cosine inverse b squared 25 plus 64 minus 36 2 times b times c. All right, so we'll discover what that one is. All right, so we get alpha is approximately 48.5 degrees. So now we can find beta. We know the sum of the angles, it's going to be approximately. The sum of the angles is 180, so we'll just subtract there. And let's see what we get for that. So we get beta is approximately 38.6 degrees. So we found these three angles. From the first two using the law of cosines, the third one was just subtraction. So now we've solved a triangle with the side, side, side scenario. Probably the most familiar equation or formula for finding an area of a triangle is 1/2 the base times the height. But you may not know the base and the height of a triangle. But in trig, we have some other formulas, and one that we can use is if you know two sides and an included angle, you can use one of these formulas to find the area of a triangle. So let's look at an example there. Suppose we have A is 5, C is 8, and B is 10. You can see that this is A and C and beta, so that's your two sides and the included angle. So the area, it's very easy to calculate, is 1/2 times 5 times 8 times the sine of 10 degrees. So let's see what that is. And that's going to be approximately 3.47 units squared, whatever your units would be. And that's how you can find the area of a triangle, very simply, if you know two sides and an included angle. If you know the measurement of three sides of a triangle, you can use a formula called Heron's formula. Now, it takes a little bit of calculation, but it's not difficult to use. First, you find a value S. That's the semi-perimeter. It's the sum of the three sides divided by 2. And then it's just a matter of substituting these values into the square root and calculating it. So let's see what we get here. So we have S is 100 plus 50 plus 75 divided by 2. All right, now again, And you could do this probably in your head, but if the numbers are kind of large or you've got some decimals, just make sure you remember to put a parentheses around your numerator, and then you'll be all right to get the right answer. Another thing you might want to do, if you know how to do it, is, and it's a good thing to learn how to do, is to store this value as x in your calculator. You can store it as a variable. So if I store x or store it as that variable, then when you enter this in your calculator, you don't have to keep writing this over and over again, entering this. You can just use those values. All right, so A, the area, rather, capital A, is going to be S. All right, so it's going to take a little while to write all this out. Minus 50. And now it's an easy formula to use, but since there's so many calculations in there, you just have to be careful, because you could definitely make a little calculation error and get the wrong answer. So you want to maybe double check your answers when you do this. And you want to put parentheses, when you enter your square root in your calculator, you want to make sure you put parentheses around the whole thing so that you don't mess up on that. So let's see, so that's, and if you put the value of S into your variable, like I said, then it'll be a lot easier to enter. So that's going to be approximately 1,815.46 square units. And that's how you can find the area of a triangle if you know all three sides.